Hi, good that you're attending this online presentation. My name is Jana Barel and I am a member of the Mixed Peat team. I work as a postdoctoral researcher in Toulouse in southern France. The Mixed Peat team loves to study peatlands, and I will be sharing one of our latest experiments with you. Let's start to talk about rain. Rain can be very boring, particularly when you're sitting inside and you're hugging your cup of hot chocolate and you're staring out of the window. But rain can also be really dramatic. The Guardian earlier this year published this photo. After very, very heavy rainfall in the French-Italian border regions, 7 people were killed because the rain caused floods and caused a lot of chaos. Well, that our weather is changing is not very big news. We know this already for some decades now, because the climate models have been predicting shifts in our climate. In 2016, this publication came out that actually confirmed that our current rainfall patterns are confirming the earlier climate models. Let's have a closer look at that. In these two graphs, the change in rainfall is illustrated. The change in rainfall in the last 100 years. In the top graph, we can see that large parts of Europe, but also Asia, are colored red. And this means that the number of dry days without rain is increasing. But in the graph on the bottom, we can see that the same regions are blue, indicating that there's actually more rain which fell in these regions. This seems contradictory, but it actually means that rainfall becomes less frequent but more intense. Why do we care so much about these particular regions? Well, they are home to peatlands. And peatlands are like our carbon guards. Peatlands are the largest terrestrial carbon stocks, and you can imagine that if the conditions are changing here, they might influence the carbon dynamics. And if the carbon dynamics change, it might have a direct influence on the climate. And that is why we are interested in understanding how peatland carbon dynamics change or respond under shifting rainfall regimes. If we want to formulate our hypothesis, we can use this conceptual diagram from 2008. Peatlands are hydric systems, so they naturally have a high water table, which is close to the stress threshold. Even though the water table will fluctuate, the system will spend a lot of time close or under anoxic conditions, as indicated by the lines that are in the white zone. When the water table drops then, and enters this gray zone, there's actually more oxygen coming into the profile of the peat. Under these normal conditions, normal rainfall conditions, these systems are usually stressed. So the productivity is not spectacularly high, but the release of carbon dioxide as a consequence of respiration and decomposition is even smaller. A process that does not need oxygen and thrives in anoxic conditions is methane emissions, so these will be high. When these systems start to experience a shift in rainfall, we might see responses in the carbon dynamics. The water table will start to fluctuate much more, and the system spends more time in this gray area, which promotes uptake of carbon dioxide, as well as increasing the respiration and decomposition rates. Methane, on the other hand, will be emitted in smaller quantities. Let's take this hypothesis one step further and think about what happens if from a period of extreme rainfall we go back to normal conditions. Well, we expect that also the carbon dynamics will be restored. Theory is nice, but practice is so beautiful. Look at this. This is our field site in the French Pyrenees, very close to the border with Andorra and Spain. We have been studying this site for some time now, so we have recordings of the temperature and the precipitation, so we can take this site as a reference. We sampled the peat and took intact cores to our greenhouse, where we constructed mesocosms in watertight containers. These mesocosms then we exposed to experimental rainfall regimes. This meant that all the pots received the same amount of rain, but spaced out differently in time. I can best illustrate that with this graph, where the bubbles are our mesocosms, and on the x-axis I've plotted how often it rains, and on the y-axis you can see how intense these rainfall events are. So the least extreme of the regimes are in the right bottom corner, and the most extreme are in the left top. These last, most extreme regimes do experience rain, but there are longer dry periods in between rainfall events, and when it rains, it pours. We exposed our pots for 12 weeks to these experimental rainfall regimes during a phase 1. That's followed by phase 2. During this phase, we re-wetted the pots, we watered regularly, and tried to restore the water table. We monitored the water table depth throughout the experiment. We studied the decomposition rates of graminoid litter that we collected in the field, and we monitored the fluxes of carbon dioxide and methane. The water table depth was really dynamic, as you can see in this graph, particularly during the first phase. It is a bit hard to distinguish any differences between the regimes in a graph like this, but if we plot them as box plots, so overall water table depths, then it looks like this. Two graphs, one for the experimental rainfall regime and the second one for the re-wetting phase. We don't see any differences between regimes, indicating that, like we planned, the overall water table depth did not differ too much. Remember that all those pots got the same amount of water, so this is the result. Because we spaced out, we had our experimental rainfall spaced out differently between the regimes, the fluctuation of the water table depth was different between regimes. So first of all, if you look at the standard deviation of the water table depth, it was much higher in the first than in the second phase. And notably, we see that regimes 3 and 6 experience more fluctuations than the other regimes. Well, how did this affect the processes? First up, litter decomposition. On the y-axis of both of these graphs, I've plotted the rates of decomposition. In graph A, we can see that there is a significant relationship with the overall depth of the water table. The larger the distance from the top of the sphagnum to the water table, the higher the decomposition rates. In graph B, we can see there's also a significant relationship with the fluctuation of the water table. And we find the highest decomposition rates if there was also a high amount of fluctuation indicated by the standard deviation. The responses of the carbon fluxes then. The exchange of carbon dioxide, we can look at that from the perspective of respiration, so how much is emitted, as well as the uptake, which I will show next. Respiration was increasing over time. This we can interpret as a seasonal trend. Respiration tended to differ between the precipitation regimes during the first phase, but not during the second re-wetting phase. The uptake of carbon dioxide is represented as net primary productivity, so the amount of carbon dioxide that's taken up as a consequence or as a function of photosynthesis. You see the values are negative, so indicating assimilation. And again, we can see a seasonal trend, so assimilation becomes stronger as time progresses, and the mesocosms spend more time under the extreme rainfall regimes. However, if we re-wet the pots, we see that the assimilation becomes less. Again, there's a tendency for assimilation during the first phase to differ between regimes. Methane emissions also show a temporal trend, so they increase as time progresses. Particularly steep is the increase when we are re-wetting the pot, so when we go from phase 1 to phase 2. And what is notable here is that in the second half of the experimental rainfall period, the differences between regimes become much larger, and one of the most extreme regimes, the pots under this regime almost stopped emitting methane completely. There is another way of looking at this type of data, and it is by interpolating all the flux rates and summing them up. So we calculated the total amount of carbon dioxide and methane that was exchanged from these pots. The net ecosystem exchange is the net effect of respiration and primary productivity combined. We see that there is a significant relationship with the fluctuation of the water table, and that if the fluctuations are high, that the pots tend to no longer be a source of carbon dioxide, but become a sink. During the re-wetting phase, we also find a relationship with the standard deviation. But mind you, these are still the fluctuations that the pots have already experienced during the first phase. So the fact that we found a relationship here means that the extreme precipitation had lasting effects, even if we restored the water table and stabilized the water table dynamics. For methane, we also find a relationship with the water table. In this particular graph, it's the mean water table depth. Highest emissions when the water table depth is very high, so close to the top of the sphagnum. The depth is shallow then, so close to the top of the sphagnum. In the second phase, we don't find such relationships, and from this we conclude that re-wetting restores the carbon methane dynamics. So this brings me to the conclusions. Well, we have seen that bringing peatlands under extreme precipitation regimes means that they start to take up more carbon dioxide, and they increase the rate of decomposition. They decrease the emissions of methane. This might seem positive, but we suspect that the increased uptake of carbon dioxide is because the lowering of the water table gives vascular plants the opportunity to develop bigger root systems, and they start to perform better and therefore take up more carbon dioxide. But the system is still losing carbon through the decomposition. It might actually be a signal that the vegetation is changing. So we'll need to look into this further to see what this exactly means. We've also seen that when we are re-wetting the system, we might be restoring the dynamics of methane, but we're not restoring the carbon dioxide dynamics. We still can measure effects from the earlier extreme precipitation regimes. If you put this into context, it means that if an ecosystem experiences extreme conditions early on in the growing season, that even though the extreme conditions lessen and it turns back to normal, we still can measure lasting effects. So even if the extreme conditions are brief, they still change the functioning of the ecosystems. And with that, I come to the end of the presentation. So I hope that you've learned something today, and the next time when it's raining, you will not immediately think about your umbrella, but you will also think about these sphagnum mosses and how rain changes peatland carbon dynamics. On behalf of the Mixed-to-Peat team, I'd like to thank you for your attention, and we welcome your thoughts and questions, so please get in touch with us. Thank you.